All right, let's go ahead and do a complete problem. So example 3 reads, imagine playing a game with money on the line with a friend with the winner, determined by drawing a single card from a standard deck of cards. Let the random variable X represent the amount that you win. So here we have a little table that says you're going to win $10 if you draw the ace of spades. You're going to win 5 if you draw any other ace. Win 2 if you draw any other spade. And then finally, you lose $1 if you draw anything else. So the parts that we see here are ABC. And the first part asks us to find the expected value. Now, to find the expected value, you have to actually create the probability distribution. So let's scroll back to example 2 on page 2. It's the exact same scenario, but this time they actually ask us to find the probability distribution of the random variable X as a table, which we need. So let's go ahead and do this. If you remember, the rules for the distribution is that you need to, one, have every single outcome be considered. So all outcomes are considered. And it's actually pretty simple for us because we have that little table summarizing all of the potential values that the random variable $10. You can also win 5, 2, or 1. Now, be careful there with the 1 because the 1 is actually not a win. So we defined X as winning, but the last outcome is a loss of 1. So it's, in effect, the opposite of winning. So we got to make sure that we write that value of my random variable with a negative in front of it, representing the opposite of what the random variable is defined as. All right, now that we got the potential values, we got to go ahead and write the probabilities of those outcomes. So what's the probability that my random variable could equal that given value? So number 1 says, what is the probability that X could be 10, right? That my random amount of win could be 10. Now, I'm going to win if I draw the ace of spades. So you don't remember, here is the, I guess, sample space for this random variable. And I'm trying to draw the ace of spades. So if I get this ace, I win $10. And that's more or less the grand prize. Now, that's a single card out of 52. So that's 1 out of 52. And if you throw that into a calculator, you'll get this to be roughly 0.192. Now, to win $5, you got to draw any other ace. So we get 5 from here, 5 from here, or 5 from here. And so notice that that's 3 different cards that would produce a winning of $5. So that's 3 ways that could occur out of 52. All right, throw that into a calculator and we get 0.0577. Let's go ahead and do the same thing for the other 2. So to win $2, you're going to draw any other spade. So remember that the suit of spades is right here. Below are the clubs. So any other spade, and remember that there's 13 in this entire row, and the grand prize is the ace. So if there's 13 in total, then there are 12 remaining spades. So that's 12 out of 52. All right, so that's a calculator, and we'll get 0.2308 roughly. So I keep rounding these to 4 decimals. All right, now what about the losing? Losing is if you draw anything else. So it's a little easy if we have this little visual summary here, because we have, we can then count the number of remaining cards. But here's the way that I want to think about this. 1 card gives a grand prize of 10, 3 cards give grand prize of 5, and 12 cards give the prize of 2. So if we add that up, we get the number of winning cards. And so adding up 12, 3, and 1, we see that there are 16 winning cards. And if there's 52 cards in total, then you simply subtract them and you'll get that there are 36 out of 52 losing cards. So throw that into a calculator and you'll get 0.6923. And there we have it. We have our probability distribution of the amount of money that we could win for this game. Let's go ahead and answer this part B, which says, is this a valid probability distribution? So it's just a really nice way of wrapping this up. So are all outcomes considered? And we basically check that by checking if you were to add up all of the probabilities that we've got over all potential outcomes. Do you get a value that's roughly 1? And here the answer is going to be yes. You guys can verify that. I think here we end up with 0.99. 7, 8, 9, 10, 11, 12. Oh no, we actually get a 0. So here I think we actually do get exactly 1. So we can check that off. Now, the second condition is that we've got valid probabilities. And the way that we check that is simply check that each probability is between 0 and 1 inclusive. And we've got eyes. We simply eyeball that, go down this column here. And we can see that the values 0.01, 0.05, 0.23, 0.69, those are all, in fact, between 0 and 1. All right, so there's our probability distribution. Now let's go ahead and answer the actual question they wanted, which is find the expected value. So remember, we use stack crunch for this. So we need to be prepared. We go ahead and make the distribution as a table. And so we just simply go ahead and record what we wrote down earlier on our paper. All right, so this would be -1, 2, 5, and 10. Perfect. So now that I've included my distribution here as a table, I can just simply go ahead and use the calculator. So go to Stats, Calc, and we'll go to Custom. There is our distribution as a table. And we can see that visually, it's way more likely that we're going to lose money. So being over here is very, very likely. Winning the grand prize, obviously, is less likely, but we've got our mean and standard deviation just right there on our little app. So let's go ahead and record that. And that more or less does it for that first part. So there's our mean and there's our standard deviation. We're going to write mu of x, or just mu, is 0.2498. As well as sigma sub x, or just sigma, is 2. All right, now remember, we have to interpret this. So this means that if you were to play this many times, you can expect to win 0.24. So let's interpret that. So interpret. That'll be a bonus. So we can expect average. Now, what does that mean? Notice you cannot win 25. You're either going to win 10, 5, 2, or lose $1. It just means that if you play this game repeatedly over, for example, 10 games, that you can expect to win roughly $2, $2 or $3. And that's simply what that says, that you'll win on average. So it's really important to include that word average. All right, let's move on to part B, which says simulate 1,000 games played by 4 different individuals. So we saw in the previous video how to simulate this. So remember that once you've got your distribution, you can simply go to Data, Simulate, and we're going to select Custom because we created this. Rows, I believe it was 1,000. And then columns, if you leave this at 1, it'll just create 1 column. So you can check. Oh, did not type in 1. So here we go. So here we see the outcome. And this was for 1,000. So 1,000 trials or games played. So here you can see that the first outcome was you lost. You lost. Hey, check it out. You got $2. And then on the next draw, you got another $2. Then you lost. And remember that the expected value says if I were to take the average of all of this that I see here, that should be roughly the expected value that we created without doing the simulation. So we did need to do this for 4. So in reality, you could just do this by doing it for 4 columns. And that just represents, so here's person number 1, all of their gameplay outcome. Here is person number 2, all of their gameplay. Here's person number 3 and number 4. So let's go ahead and just find the average of that. So we'll go to stats, summary stats, columns. And I'm going to go ahead and select custom 1, 2, 3, 4. I really only care about the mean. We know that this is 1,000 per person. So here is my summary. And let's just note that for player number 1, after they played 1,000 games, their mean actual average of the sample that we've got in our column is 0.329. The mean of customer 2 is 0.19, mean of customer 3, 0.27, and customer 4, 0.22. Notice that this was only for 1,000 games per person. And note how all of these values are more or less slightly above or below the theoretical mean of 0.25. So I'm rounding it up. So you can see that this does tend to agree with that theoretical value. And hopefully this helps to clarify what expected value is with that actual example. So we did go ahead and find the sample means. And now here we interpret the expected value. So if you play 1,000 games, how much would you expect to win or lose? So remember, winning or losing would be how much money you come out winning or losing here. So if you were to stop the game after 10, so here you lost $1, lost $1, lost $1, lost $1. So that's $4 gone. But then I won $2, then I won another $2. So here you've come across with $0 in total. Then you lose, and then you win. So you really only come out $8 ahead by this point. On your final trial, you get another 5. So that's $13 that you win total. We can actually compute this. Let's actually do that. Let's go to data, compute an expression. And what I'm going to do is I'm simply going to sum. Let's actually find the function here, sum. Right, so there's a sum, and then I'm going to find, click on custom 1. Make sure it's between the parentheses. All right, and so there it is. Look, the amount of money that I won for player 1 was 329. Let's go ahead and edit this and change right here, custom to 2. Edit this again to 3. And again, finally, let's change this number out here to 4. Now, if we take a look at the rows that we created, we basically have the net amount of winnings for all of these customers or players after 1,000 games. So we see that after 1,000 games, player one has a net sum of 329 as the winnings, player two, 191, player three, 273, and player four, 220. So this is an actual simulation of how much they would walk away with. And notice that it's positive. So they're actually winning after this. So I already interpreted the expected value. We can expect to win roughly 25% per game on average. So if I play 1,000 games, that's the number of games. And then I'm simply going to multiply that by the expected value. Because remember, the expected value tells you the amount you win per game. So we're simply going to multiply 1,000 by 0.25. And you can throw that into a calculator and you get 250. So this is saying that if you play 1,000 games over and over again, kind of like what we did here, we saw 4 people do it. But if we, for example, took 50 people that did it, the average of the winnings, so that's these numbers here. So I can basically get the average of that. So here, let's call this winnings. And they were what? 329, 191, 273, and 220. So let's find the average of that. And take a look at what we just got. Over those 4 individuals, the average of those 4 winnings is 253. That is very close to what we said here. If you play 1,000 games, you expect after those 1,000 games to have, for example, $250 in winnings. And you can see that that's very close with this simulation here, 253. Obviously, when you simulate this, all of your values will be different. All right, that wraps it up. Please make sure that you take a look at this example again. It has a lot of concrete examples as well as just demonstrates how you complete these problems. All right, thank you for your time. I'll see you in the next video.